In this video, we're going to discuss how quantifiers are used in logic and mathematics. There's a lot to be said about quantifiers, and we're just going to be scratching the surface, but hopefully this video will be enough to get you started. So a statement such as x squared equals 9 is not a logical statement. So remember that a logical statement is a declarative sentence that is unambiguously true or false. But x squared equals 9 by itself, without more information, it's not clear if it's true or false. We need to know more about the variable in particular. So we're going to discuss three ways to qualify a statement with variables so that it becomes a logical statement. So the first thing we can do is we can simply specify the value of the variable. So for example, if I change the statement from x squared equals 9 to the statement for x equals 3, x squared equals 9, then that becomes a logical statement, and in fact a true logical statement. On the other hand, if I change the statement to for x equals 4, x squared equals 9, well, it's a logical statement, but it happens to be false. So one thing you can do is you can specify the value of a variable in order to make it a logical statement. So we're going to focus mostly though on quantifiers. So we can also qualify variables with what are called quantifiers. There are two quantifiers. There's the existential quantifier, which is the phrase there exists, as in there exists x in the natural numbers such that x squared equals 9. Notice that the phrase there exists is followed by a clause and then the phrase such that. That's the typical grammar that's used. That becomes a true logical statement if we make that statement. We also have the universal quantifier for all, as in for all x in the natural numbers x squared equals 9. Now, that's a false statement clearly, but it is a logical statement. It's unambiguously true or false. Okay, it happens to become a false logical statement. However, we can have true statements, of course, with universal quantifiers. So consider the statement for all n in n is less than n plus 1. Okay, that's a true logical statement. So we have two quantifiers, the existential quantifier and the universal quantifier, that we're going to be discussing in the rest of the video. Now, mathematical statements very frequently contain these phrases, for all and there exists. In fact, mathematical statements often contain more than one of these phrases. So for example, this statement is known as the Archimedean Principle. For all r in R, so for all r in the real numbers, there exists an n in the natural numbers such that r is less than n. So you can see there, this statement contains the phrase both for all and the phrase there exists. Now you'll often see for all abbreviated with the symbol upside down A. And the symbol upside down A, the quantifier, that's called the universal quantifier. And the phrase there exists is often abbreviated with a capital backwards E. And that quantifier is called the existential quantifier. And so the statement of the Archimedean principle, for all r in the reals, there exists an n in the natural numbers such that r is less than n, that could be rewritten with the quantifiers upside down A and backwards E, and you'd still read it the same. You'd still read it as for all r in the real numbers, there exists n in the natural numbers such that r is less than n. Okay. Now sometimes the phrase such that, which you see often, is abbreviated with just s period t period, so just abbreviated st, or sometimes you see this backwards epsilon used. So you might see the Archimedean principle or other statements with existential quantifiers written with those abbreviations. So you might see for all r in R, there exists n in n, st, meaning such that r is less than n. And also if it has the backward epsilon, you also read that as such that. So, as is often the case in English, there's more than one way to say there exists and for all. For instance, you might see or even say there is instead of there exists, or for every instead of for all. But don't fret, these mean the same as there exists and for all, at least in mathematical discourse when we're doing mathematics. There are some phrases that you should avoid, like any. It's usually sometimes any means one and sometimes any means all. but you should stick with for every or for all or there is or there exists, and those mean the same as our usual existential and universal quantifiers. Now, one thing to notice that we haven't pointed out yet is that quantifiers typically come with a range or a scope of potential values. So for example, in this statement, for all r in the real numbers, there exists n in the natural numbers such that r is less than n. The for every quantifier, the for all, says for all r in the reals. And the existential quantifier says there exists an n in the natural numbers. The range of possible values for a quantifier is very important. It's an essential part of the meaning of a statement. And so for example, the phrase there exists x in the rationals such that x squared equals 2, that's a false statement. That's not true. There's no square root of 2 in the rationals. Okay? But if I just change the scope of that quantifier to the real numbers, then it becomes a true statement. Okay? So don't ignore that range where the variables come from when you're restating or reformulating a mathematical statement with quantifiers. One thing that often occurs is mathematical statements frequently occur with hidden quantifiers. So for example, this statement, the function f of x equals x squared minus 9, has an integer root. Well, that has a hidden existential quantifier. It's claiming that something exists. So you can reformulate it as an existential statement with a there exists quantifier in it. So we can rewrite this as there exists x in the integers such that f of x is equal to 0. The statement f of x, the function f of x equals x squared plus 1 has no real roots. Okay, so see, we can reformulate that. Really what we're saying is no real number makes that function 0. So we can say there does not exist, so not there exists a real number such that x squared plus 1 equals 0. Okay, so that's a way that we could rewrite this to make that hidden quantifier explicit. Notice that this statement, it's not true that there exists a real number such that x squared plus 1 equals 0. That statement is logically equivalent to, has the same meaning as at least, for all x in R, x squared plus 1 is not equal to 0. Okay, so this is an instance of negating quantifiers, which we're going to talk about below. Be on the lookout for hidden quantifiers. They often occur in mathematical statements, and always try to translate them into statements containing the appropriate quantifiers, because that's really going to be essential to getting started in proving those statements or understanding their meaning more clearly. Now let's talk about how we prove statements with existential quantifiers and statements with universal quantifiers by first talking about how to prove that something exists. Usually, if you need to prove that something exists, you need to build the object that's claimed to exist and show that it has whatever properties it's claimed to have. So for example, here's an easy theorem that if you have an ordered field F and A and B are elements of that field with A less than B, then there exists an R in the fields between them, so that A is less than R is less than B. So notice that this is a statement that's claiming something exists. In this proof, as is often the case, to show that something exists, you need to build it and show it has the appropriate properties. So let's suppose that A and B are elements of the field. Let's suppose that A is less than B. Then we can just build the element R by just taking the average A plus B over 2. Okay. Then I'm going to leave it to you to verify that A is less than R is less than B. Really a foolproof if we weren't sort of pressed for time as in this video, would demonstrate that R is really between A and B. You know that the average is between those two numbers, but it would be appropriate to verify that in the proof. Now, sometimes to prove that something exists, it's a little bit tougher. We need to do a little bit of scratch work outside of the proof to show that it exists. And we don't want to bring that scratch work into the proof. So for example, let's consider this statement. For all real numbers x less than 1, there is a natural number n so that x is less than n divided by n plus 1. Okay, so we're claiming there exists a natural number n so that x is less than n over n plus 1 if x is less than 1. So here we need to find a natural number with a particular property. All right, and so we need to build that natural number. We need to find it somehow, and we need to show it has the correct properties. So how do we do that? Well, let's work backward for a minute. So this is something that would never go into a proof, this working backward business. It's not logically the right direction to go, but let's just play around with it for a minute. So if we know that x is less than n over n plus 1, what are we going to do? Well, let's multiply both sides by n plus 1. That gives us x times the quantity n plus 1 is less than n. So might as well distribute through. That gives us x times n plus x is less than n. So x is less than n minus xn. All right. So x is less than n times 1 minus x, pulling the n out on the right. Okay, so maybe the proof would work then if we could find a natural number larger than the real number x over 1 minus x. All right. So let's see. So that seems reasonable. 1 minus x. We know that x is less than 1. So in particular, x is not 1. So x over 1 minus x is a well-defined real number. So let's think about that. Can we find a natural number larger than a given real number? Yeah, we've been talking about the Archimedean Principle in this video a lot as an example of the use of quantifiers. So to answer the question, can we find such an n? Yeah, we can by the Archimedean Principle. Okay, so we did some scratch work to get a condition that, oh, we can satisfy that condition. Now that scratch work's not going to go into the proof, but it just shows how sometimes to show something exists, you need to build it, and that process of discovering it is not a process that you would include in your proof. You would just assert that you can do this and then go on with the proof. So let's see how that works. Let's try to rewrite this then as a proof. So here's our lemma. For all real numbers x less than 1, there exists a natural number n such that x is less than n over n plus 1. So suppose that x is a real number and x is less than 1. By the Archimedean principle, then, there exists a natural number n so that x over 1 minus x is less than n. Remember, x over 1 minus x is a real number. Since x is less than 1, we know that 1 minus x is greater than 0. So we can multiply both sides of the inequality to obtain x is less than n times 1 minus x. That product doesn't change the direction of the inequality because we're multiplying by a positive number. So x is less than n minus n times x. So you can see we're going in the reverse of the direction that we did in our scratch work, because we're going to wind up with the condition x is less than n over n plus 1. Okay, so x plus nx is less than n, just adding nx to both sides. So from this condition we can pull out the x, we get x times 1 plus n is less than n, and therefore x is less than n over 1 plus n. So we proved that if x is a real number and x is less than 1, then there exists a natural number n such that x is less than n over n plus 1. So notice that our scratch work, again, just to emphasize this point, the scratch work we did to find n, we had to reorganize it to present it as a proof. And that's not an uncommon situation when you're proving that something exists. Now what about universal statements? So let's suppose we want to prove the statement for all x in the set S, p of x is true. Okay. So notice that we can restate this. So that's a universal quantifier. It's saying for all x in the set S, that's a universal quantifier. We can restate that as if x is in the set S, then p of x is true. Okay. So for example, consider this statement. For every prime number p, p plus 7 is a composite number. All right. So that's similar to what's going above. So it's saying for every p in the set of primes, p plus 7 is composite. Well, what we can do is we can reformulate that. We can reword it as if p is a prime number, then p plus 7 is composite. And then that's kind of gives us a clue as to how to start the proof. Okay, so we can begin the proof of an implication by assuming the hypothesis. Okay, so let's do that. So now we've rewritten this to state if p is a prime number, then p plus 7 is a composite number. So let's assume p is a prime number. Notice that if p is a prime number, then either p is 2 or p is odd. If p is 2, then p plus 7 is 9, and that's a composite number. On the other hand, if p is odd, then p is equal to 2 times k minus 1 for some natural number k. And if we add 7 to that, we can see that becomes p plus 7 becomes 2k plus 6. We can factor out a 2, and then it's 2 times some natural number. So p plus 7 is 2 times another natural number, so it's even. And even numbers other than 2 are composite, so we conclude that p plus 7 then is composite if the number p is prime. Okay, so there, that proof, we got started by rewriting the universal sounding statement as a conditional statement, as an if-then, and that allowed us to get a sort of a handhold on where to start the proof by assuming the hypothesis. So this occasionally works the other way in this following sense. So let's suppose that we need to prove a statement that has the logical form of the negation of an implication. So it's of the form not p implies q. There's really no nice logical equivalent to this statement that works very well. You could go through the process of writing the implication as not p or q, and then negating that to get p and not q and trying to prove that. But again, it can get a little bit clunky, so that's certainly a procedure. But one nice thing you can do is the following. If we can rephrase p implies q as a kind of universal sentence, as saying for all x in some set S, p of x is true, then we'll see below that there's a nice way to negate a quantifier, and that will help us get started on the proof. So in this case, as in many cases, it's often helpful to negate mathematical statements when considering whether they're true or false, or when developing a proof strategy for the statement. So let's suppose p is a logical statement. Then we write the negation of p as this kind of left, this L, this sideways L, or with a tilde, as we've seen in earlier videos. And we read it as not p. But really, if you have a mathematical statement or English sentence you're trying to negate, it's usually better to restate it with better grammar. Okay, and with quantifiers, that works as follows. So let's say you have a statement claiming that there exists some element x so that p of x is true. The negation of that is for all x, not p of x. Okay, so that would say that p of x is not true for any x. So if the statement says there exists an x for which p of x is true, the negation of that is that p of x is not true for any x. On the other hand, if the statement claims for all x, p of x is true, the negation of that is that there exists an x for which p of x is not true. So p of x is not true for some x. Okay, so let's write that as a theorem. Let S be a set, and let p of x be a mathematical statement defined on the set S. Then the following pairs are logically equivalent. The negation of for all x in S, p of x, is logically equivalent to there exists an x in S so that p of x is not true, or not p of x. And the negation of the statement that there exists an x in S such that p of x is true, the negation of that statement is logically equivalent to for all x in S, not p of x. All right. So it's important to recognize that the order quantifiers appear in a statement is very important when the statement contains both existential and universal quantifiers. So for example, this statement, the Archimedean Principle, for all r in the real numbers, there exists n in the natural numbers such that r is less than n, that says that the natural numbers are not bounded in the reals. Okay, so that's true. For any real number, you can find a natural number larger than it. On the other hand, if you were to reverse the order of the quantifiers, you'd get the statement there exists n in the natural numbers such that for all r in the real numbers, r is less than n. And that means something entirely different. Okay, if you think about the meaning of that, it says that the real numbers are all below some natural number. It's saying that there exists a natural number so that all real numbers appear below that natural number. Okay, and that's clearly false. That's not a true statement. So it's really important to pay attention to the order of the quantifiers in a mathematical statement, because reversing the order or changing the order in some way will change the meaning of the statement. Okay, what about statements where you have two quantifiers? So notice that if you have a statement of the form, for all x there exists y so that p of xy is true, the negation of that, you flip both quantifiers, so you change both quantifiers and negate the statement. So if the statement is for all x there exists y so that p of xy is true, the negation of that is there exists x such that for all y not p of x. So to interpret the negation, that would mean for some x, p of xy is false for all y. On the other hand, if you have a statement like there exists x such that for all y, p of xy is true, the negation of that would be for all x there exists y so that not p of xy, which to interpret that would mean for all x, p of xy is false for some y. Okay, so it takes some practice to get used to using quantifiers and negating quantifiers. Hopefully this video will get you started on it. That's it. Thanks for listening.